Welcome to Physics 2 Lab 1 Charged Tape by me, Pratham Mingale. Introduction. We want to see how two charged pieces of Scotch tape interact with each other using principles of electric fields and gravitational forces. I want to model the interaction with Python in Glowscript and compute various calculations such as the charge on the tape and electron deficiency. Speaking of electron deficiency, we want to find if the charged tape is electron deficient or excessive, and then calculate how the atoms interacted with the electrons and the ratio. So the results that I found, the charge on the tape is 5.629 nanocoulombs. The tape has an electron deficiency of 3.518 times 10 to the 10th electrons, and the tapes repel when close to each other, meaning that they have like charges. We can see a model I got from Glowscript, tape B, tape A, going up, going down. Introduction continued. Let's talk about the physics. So, three main laws. These two represent the forces. We have the gravitational force, and we have the Coulomb's force, or electrostatic force. And we both know how these work. Let's go to this one. Newton's second law of motion says the sum of forces equals mass times acceleration. We know that there's no acceleration, meaning that forces, or the sum of forces, is zero. So, assuming this is the piece of tape, there's the electrostatic force up, gravitational force down. We know that these two forces are equal, and we can use that to solve for specific values such as Q. Let's go to the system. So the system is tape B, which is supposed to be up here. This is tape B up here, the top tape. This is wrongly labeled. The surroundings are tape A and the floor, but mainly just tape A. Initial conditions, you can see here, tape length is 0.172 meters, tape width is 0.019 meters, tape mass 1.72 times 10 to the negative fourth kilograms, and initial charge. Both are neutral with charge 0. We charge them on the table after the experiment starts. So let's go into the actual experiment. We found the distance d between the two tapes to be 0.013 meters, as you can see up here. The charged tape was attracted to various objects, such as my hand and a pencil, but it was repelling the other charged tape, as you can see it rising here. Experiment, let's go over how we did the experiment. One piece of tape was mounted on these two boxes, and then another piece of tape was brought underneath it to observe how the top one moved. We took care to conduct the experiment quickly to not lose as much charge as possible in the two tapes, and we measured the distance by recording a video of the experiment and propping a meter stick right next to it, and then watching the video back to see the distance. The coding model is over here. We can see that we started by finding the gravitational force by using mg, and then the inverse of that, or the negative of that, is the electric force, because we can see here the forces cancel out, there's no acceleration, and with that we can find what the electric force is, the magnitude of it, and then go from there, reverse engineer to find what Q is, because we know all the other values present in the equation. Once we have the charge, we can find the number of electrons, the number of atoms, and the ratio. And we can determine that the charge is 5.629 times 10 to the negative 9th coulombs. It's electron deficient, and the ratio of atoms to electrons can be displayed here. Comparisons and assumptions. There aren't many differences and similarities between the two models because we use the data from the observational or the actual experiment to guide and drive the calculations in the computational model. But there were two main assumptions that we did make. We assumed that the charges were point charges, unlike the tapes that we use where there's a lot of charge spread out across the tape. And we also assumed that the tapes were identically charged and evenly charged, which means that we don't know if this part of the tape is charged the same as this. We don't know that it's uniform, but we're assuming that it is. And we also don't know if both tapes have the same charge, but we are both also assuming that it is, because otherwise this Q and this Q would be different. Sources of error. There are three main sources of error that I've identified. The first one is air resistance. The tape is not aerodynamic, and the air might have an effect on how high it can raise in response to electrostatic force. Loss of charge. There's a chance that when the tape was in contact with human hands or the mounting boxes, the tape might have lost some charge, resulting in a situation where the charge changed halfway through the experiment, or the charges are different on the tapes. The weight of the tape was also estimated and not measured by a scale, meaning that the gravitational force calculation may be slightly off. What if and why questions. What if the electrons had positive charge and the protons had negative charge? Nothing would change. The charges, like charges, still repel, and opposite charges attract. Since the two tapes repel each other, we know that they both have the same charge, same direction of charge. Why is it important to handle the charged tapes as little as possible? It's because when you're in contact with them, they're constantly losing or gaining electrons to outside surroundings. So your hand or other objects might be taking or giving electrons to the tape and manipulating their charge. And yeah, that's the end. Thank you.